Hello everyone, this is Nabil from Midas IT India. So this training is all about bridge piers and abutments, one of the Midas training series. So I hope you all will enjoy the training. So basically piers and abutments are an integral part of the load path between the superstructure and foundation. So in multi-span bridges, the ends of superstructures are supposed to be over the abutments, whereas the intermediate spans will be resting on the piers. So basically, piers resist and transfer vertical and horizontal loads to the foundation, and abutments, in addition to it, will be retaining the embankment also towards the end. So the classification of piers. So piers can be classified on the basis of the connectivity with superstructure. So they can be of monolithic or integral type, or secondly, they can be of cantilever type based on the superstructure and substructural separation. If they're separated by bearings, then they'll be cantilever type. Another classification can be done on the basis of sectional shape and framing configuration. So the first one is solid type, the second one is trestle type or the bent columns. The third type is the hammerhead type, and the fourth type is the frame type. So for the first type, solid hollow, and cellular type, they can be of different cross-sectional shapes, and they're often used as for water crossings, as they can be constructed to proportions that are both slender and streamlined. So for the massive piers carrying multi-lane traffic, it is economical to use this cellular type piers, so wherein we can save a lot of concrete and we can have a required amount of inertia for resisting the bending moments. So the second type is the trestle type piers, which comprise of reinforced concrete columns with a connecting cap at the top. So they can be either used to support a steel girder superstructure or can be integral. So this bent cap can be integral with the superstructure. So in that case, it will be a cast in place construction. So these trestle type piers are the most popular type piers for the modern highway system. Then moving to the third type, which is the hammerhead type pier. So a hammerhead type pier consists of a massive single pier with cantilever pier caps on opposite sides, or it can be a one-sided cap also. So the sides of the pier caps will be resembling the head of a hammer. So this type of pier is generally suitable for elevated highways, and even if they're used in river bridges, they provide minimum restriction of waterway. In addition to the concrete piers, these both types, trestle type as well as hammerhead type, they can be steel concrete composite sections also. Then coming to the frame type, so they are aesthetically superior and rigid due to the monolithic joints between the vertical and inclined horizontal members. So these type of piers ideally are suited for reducing the span length. So what you're seeing over here, this is the longitudinal cross section of pier. So they can reduce the span length of the main girders on either side, thereby resulting in cost saving of superstructure But due to the multiple joints, that is one of the disadvantage of this kind of piers. So it will increase the maintenance cost. So moving on to the type of abutments. So these are the type of abutments. The first one is the closed type or high abutments, which can be of wall type and counterfort type. And the second type is stub abutment or perched abutment. The third type is pedestal type or spill-through abutments. And the fourth type is where the superstructure and substructure will be integrated with each other, the integral abutments. So describing the closed type abutment, you can see over here. So this is the wall type and this is the counterfort type. So closed cantilever abutments consists of a vertical arm or a back wall, which will be fixed to a horizontal base, the horizontal footing. So the lateral thrust of the earth pressure, which the abutment will be supporting, will be resisted by the cantilever action of the stem and the footing. So the stem transfers the vertical load of superstructure also to the footing. So this again will be providing resistance. The dead weight of stem will be providing the resistance against the overturning of the cantilever closed abutment. So full height abutments are constructed at a lower level, lower roadway level. So they'll be supporting the whole backfill. So they are costly and they are generally used in congested urban areas where the structure depth is a critical issue. Again, one more addition to a wall type is a counterfort type, wherein the counterforts are the addition. These rectangular uh, blocks. So these are called counterforts. So they are very similar to the cantilever type abutments, but in addition, these triangular cross walls will be added, which will be connected to the stem. So this will be providing resistance against the bending, which will reduce the reinforcement in stem. So moving to the second type, which are the stub abutments. So you can see this is with stub abutment with spread footing, and this is with piles. So stub or perched type abutments are relatively short abutments compared to the cantilever abutments. So they are constructed after the embankment is completed. So this will reduce the post-construction settlement, and they may be resting on shallow footing or pile footing depending on the type of strata available. Moving to the third type, which is spill through or pedestal type. So spill through abutments are short stub abutments which are supported on multiple stems. So the pedestals or stems will be extending below the ground level. So they are very similar to again the cantilever type, but the stem is not like a wall, a complete wall. So there'll be voids in between the stems. So that will allow the lateral earth pressure to spill through the abutments. So that's why the earth pressure will be very less compared to a full heighted closed abutment in this case. Again, moving to the fourth type, integral type of abutments. So integral abutments are connected to the superstructure rigidly without any joints for the expansion or contraction. So again, an integral abutment can be a wall type abutment, or they can be a stub type abutment resting on the flexible piles. So the major advantage of integral abutments is the lower construction cost as well as maintenance cost. But again, the biggest problem with the integral abutments is the cyclic lateral expansion of the deck of the superstructure. So this expansion and contraction will be due to the temperature variation mainly. So which can result again in the cracking and buckling of the abutment stem. So these forces have to be critically assumed during design to avoid these kind of issues. So coming to the design part of pier. So the design of a pier or column is performed to fulfill strength and serviceability requirements. So for the design of piers, first step is to calculate the design loads acting on the pier. So these loads include the given set of design loads. So the red loads, the live loads, and their impact from the superstructure, and then the wind loads on structure as well as live loads, wind loads on the substructure, and then the centrifugal forces from the superstructure, the longitudinal force from live loads, the braking and traction effect, again the drag forces from the bearings, the ice pressure, earthquake forces, thermal and shrinkage forces, forces due to the settlement of foundations. If the structure is continuous, then this will be producing huge bending moment in the piers. And then the collision loads, which may include vehicle collision or ship impact. Again, so in case of capped piers, wherein a cantilever or corbel pier may exist. So based on this span, this A to D, the cantilever span to the depth ratio of the pier cap, it is decided whether it is a corbel or a cantilever. So if it is lesser than 1, then it is corbel, or if it is greater than 1, then it is cantilever. So accordingly, the design is performed. So if it is a corbel, then we adopt strut and tie method for design. And if it is a cantilever, then a general flexure design is performed for the pier cap. So moving on. Again, a pier as a structural component is subjected to combined forces of axial bending and shear. So a pier, for a pier, the bending strength is dependent on the axial force, and the bending moment will be magnified by the axial force due to P delta effect, which is second order effect. So to consider the second order effect, we first have to calculate the slenderness ratio, which is nothing but the ratio of effective length of the pier divided by the minimum radius of gyration. So the slenderness ratio is then compared with the limiting value based upon different codes, different limiting values exist. So they are classified whether they are short or they are slender columns. So if as per ASHTO code, if the slenderness ratio exceeds beyond 22, so we need to consider the slenderness second order effect. So the actual bending moments will be magnified. So here you can see this is the magnification required. So we need to calculate the delta B and delta S and multiply it with the moments coming on the piers. So again, if the slenderness ratio is more than 100, then we need to carry out a detailed nonlinear analysis for the pier. So again, for calculation of flexural resistance, the combined axial and bending strength of concrete. So this equation, as per ASHTO code, gives us the pure compression resistance of the pier. And for let's say for pure flexure, when there is no axial load, which is actually not a practical case, but for pure flexure case, this is the bending moment which is given by the code. So this is the maximum load carrying capacity of the pier, and this is the maximum moment carrying capacity. So for two directional bending, that is biaxial bending, we carry out interaction check wherein we calculate the actual moments which are coming from by combining all the loads, the loading effects, and then we divide it by the resistance of the in individual directions. So then we calculate and sum up and check whether it is lesser than 1. So this is the interaction check which we perform for the piers. So again, for that we need interaction diagrams. So basically, this is an interaction diagram wherein point A represents this equation which was having pure compression. So this is pure compression point, and this is the pure flexure point, point E, which we have shown earlier. So this equation MR represents this moment over here. So from point A to C, compression failure occurs, and from point C to E, tension failure occurs. So point C represents balanced failure condition, wherein the strain distribution for the extreme concrete fiber stress reaches the yield strain of 0.003, and the strain in reinforcement also reaches the yield point. So at this condition, the section is having the highest moment carrying capacity. Again, for shear strength of piers, the nominal shear is computed by the addition of these three components, which are the shear contributed by concrete, by the shear reinforcement, and by the pre-stressing reinforcement. So here, this should be lesser than 0.25 FC dash into the effective width of web into the effective shear depth, which is taken as the distance between the compressive and tensile forces. So again, first we calculate the shear in concrete, which is given by this equation, where beta is the factor for which indicates the ability of diagonally cracked concrete to transmit tension as per clause S 5.8.3.4. So this is taken generally as 2 for piers, and the shear resistance due to steel, if we are providing stirrups, if we are providing, let's say, links or spiral reinforcement, is given by this equation, wherein the alpha term over here is the inclination of the links, which is generally 90 degrees, and theta is the internal inclination of the diagonal compressive stresses, which is generally taken as 45. So combining Vs and Vc, we get the final shear resistance of the column section, which is again compared with the ultimate shear force, which we get after combining the design forces effects. So coming to the design of abutment, again the same set of loads are there for the abutment. In addition, we will be having earth pressure loads. So for the design of abutment, mainly there are three components. So we are having the complete stem portion and the toe portion and the heel portion. So the dimensions of the footings are based on the pressure check, the base pressure check. So wherein the complete pressure check is carried out as per the equation. So the vertical force by the complete area upon the moments, corresponding moments in the longitudinal and transverse direction divided by the Z values. So in order to assure that there is no tension at the bottom, we carry out these checks, which are stability checks. So these stability checks are corresponding to various modes of failure and for factor of safety against sliding. The ratio of total vertical force to the horizontal force is taken and it is ensured that the ratio is greater than 1.5. And then for overturning, again the overturning moment and the resisting moment is calculated at the toe end, and then the ratio is taken, the ratio of the resisting moment divided by overturning moment. So this should be lesser than 2. And the third case is the bearing failure case. So the resultant of that moment we take, where is it acting over the footing, and that should be within b by 6, the width by 6 distance. So within that distance the resultant should be acting. Again, the maximum bearing pressures at heel and toe are calculated using this equation which I have shown earlier. So this is calculated and then they're compared with the ultimate bearing capacities, and towards the toe portion we ensure that there is no tension, at the toe location. So for the calculation of design loads in abutments, so first we select preliminary dimensions for the abutments, the back wall, the stem and toe and heel of abutment. And then we compute the dead loads from superstructure. So all the loads which we'll be calculating, those loads will be for per unit length of the abutment. So we'll be carrying out design for per unit length of the abutment. So the dead load from superstructure is taken, and the dead load for back wall, stem unit, footing, and the backfill, which is the earth fill, is also taken. And then we calculate the live load effects. So wherein dynamic load allowance and multiple presence factor, which is dependent on the number of loaded lanes of the bridge, are taken into consideration. So first of all, the back wall live load as per the width of back wall is calculated, and it is calculated by placing the design truck axles and including the dynamic amplification factor and multiple presence factor. And again, we calculate the live load coming from the superstructure. So we take up the maximum girder reaction for a single lane vehicle load, and then the UDL lane loading, and we calculate the maximum reactions due to the vehicle load and the lane load, and the minimum reactions due to the same. And then we calculate the maximum load combined load based on the formula, wherein we combine it with the dynamic allowance. So we get the maximum load for single lane. So for n number of lanes, we just multiply with the number of lanes and the multiple presence factor, again depending on the number of lanes. And then we divide it by the length of abutment. So we get load per unit length. Again, the same thing is done for the foundation design, for load calculations for foundation, but we don't consider dynamic allowance factor for the foundation design. Again, if the abutments are provided with longitudinally fixed type bearings, then the abutment will be resisting the bearing force as well. So the total braking force is computed based on the number of design lanes in the same direction. As per different codes, we follow different braking forces. So as per ASHTO code, it is taken as 25% of the truck or tandem load, or a combination of 5% of truck or tandem load and the lane load, the lane UDL load. Then for the wind force, again, if the bearings are fixed, so we'll have to consider the longitudinal forces from superstructure. But anyhow, we need to consider the transverse forces from the superstructure. So again, it depends on the direction of wind. So, so over superstructure, the wind forces are calculated over the structure as well as over the live loads. And then over the substructure, as per the exposed portion of pier, a portion of abutment, it's calculated. And then the vertical wind load effect over the superstructure is calculated and is taken if the vehicular live loads are not being considered. So this is the procedure. First, we calculate the exposed area of this, the superstructure, or if we are taking abutment, and based upon the height from the ground level, we calculate the design velocity and the wind pressure, which is again multiplied with the exposed area, and then we get the final force. Again, for various wind attack angles, we get various forces. So we tabulate the longitudinal and transverse wind forces for different angles. And then coming to the earthquake loads. So as per ASTO LRFD, the first of all we see in which seismic zone the structure is falling, and as per that the applicability is checked. And again, the minimum connection force between the superstructure and substructure uh, is ensured by ensuring the minimum width sheet requirements. And again, the earth forces are calculated. The horizontal earth pressure is calculated by Ka gamma H, Ka gamma into Z, wherein K is the active earth pressure coefficient, which we generally get from geotechnical data. And then gamma is the density of the backfill material, the backfill soil, and Z is the overall height. So this calculation is done for the backfill height, for the stem height, as well as for the footing height 3 times. So the same thing is repeated for the live load surcharge load also. So for live load surcharge, the H equivalent is given by the load. So in case of ASHTO load, it's given in the table 3.11.6.41. So it's given based on the backfill height. Again, the temperature loads due to the expansion and contraction of the superstructure are considered by calculating the thermal deformation. So the thermal deformation again, it's given by epsilon delta T into L, wherein the epsilon is stands for the thermal expansion coefficient, delta T is the temperature rise or fall, and L is the overall length of the bridge superstructure. And then this deformation is used further to calculate the force on the bearing as per the bearing properties. So you can see here the shear modulus. In case of an elastomeric bearing, shear modulus is used, and the planar area. So finally, after getting all the force effects from the superstructure and the foundation, we combine all of them. So there are three critical load locations where the force effects needs to be combined appropriately and analyzed for an abutment design. So these are based upon these are basically at the bottom of abutment back wall, and then at the bottom of abutment stem or the top of footing, and at the bottom of footing. So the maximum and minimum bending moments and shear forces are calculated based on the service limit states, and flexure and shear designs are carried out accordingly. So thank you for attending the training. So this was all about the basics of abutment and pier design. So what you can do is you can just try out designing the pier and abutment. In the pier design is possible as per various codes in Midas Civil. So those designs can be compared the values of various inputs. You can check like the slenderness ratio, the the second order moments which is being taken. So all these formulas, the basics are over here. So you can just refer back the presentation and you can understand the design basics. So that's all for the presentation. Thank you.